All right. Welcome, everybody, to today's web seminar. We're going to talk about solar electric investment analysis. This is part two. We're going to be talking about the value of electricity, which I think is one of the most critical pieces for this web seminar series, but also one that seems simple until we get into the details of it. And you'll start to see why modeling these systems is really one of the only ways we can try to estimate the value of electricity being generated from them. So my name is John Hay, and I work for the University of Nebraska Extension. And we also have with us Eric Romick from Ohio State University. And we are both educators that work on solar energy issues in our states. And we have a grant sponsored by the North Central Region Sustainable Ag Research and Education through the USDA. And we are trying to teach people like yourselves and others that end up communicating about solar and giving advice related to solar to farmers, particularly small farmers. So that's kind of the audience we're trying to reach, but this information is very relevant for on-farm solar, solar at any business, as well as solar and residential. So you can apply this knowledge across those different realms. So we're going to try a couple things today, a little bit that's different than the last time. One of the things we're going to do is we may ask some questions of you, and the easiest way to answer is that in your menu bar, you can click on participants and you'll see the list of participants, but also then you'll see there's some little circles at the bottom: yes, no, go slower, go faster. And really we're interested in the yes, no. And so we'll ask you some of those yes, no questions. And if you click on it, it'll put a little check mark by your name, and we can then kind of just get some little bit of interaction that way with some real simple questions. Shouldn't be anything too strenuous that way. So we're going to go ahead and get started on our presentation, and Eric will do the second half when we talk more about incentives and some other details like that. This is a 4-part web seminar series. If you want the written version, we have that up on our SARE website, which which is actually a 6-part bulletin series that we have put together that details mainly what we're doing in written form, so that can be a reference for you, as well as we'll have these videos recorded. We're in part 2, and we're going to go through part 3 and 4. And for this particular web seminar, we're going to spend more time with the model than we do in other seminars. We're hoping that that might be useful to you as you advise farmers about solar. We're going to talk about the value of electricity, get into net metering, which is a form of subsidy, but it really influences the price of electricity. We're going to talk about how policy and subsidy impacts that value of electricity. Then we're going to cover the incentives in detail and talk about some of the cash flow mechanics. When we think about electricity, you might think about your electric bill that you get at home. And sometimes your electric bill has a lot of detail, and sometimes it doesn't. And it's important to understand that there are 4 main kind of categories that we can put most of those charges in our electric bill into. Some bills don't have all 4, particularly the one on the bottom here. The demand charge isn't in all bills. That's mainly in larger commercial bills, but we're seeing it more and more across the landscape. There's going to be a fixed charge. That charge might be from $8 to $50 or $60, depending on the size of your electrical use. But it is a charge where if you use no electricity, you're still going to get charged that value. And that is a charge that they're there to kind of cover their overhead and to cover some of the maintenance of their system. And particularly the system would be the electrical grid components themselves. There's an energy charge, which is the charge that is per kilowatt hour, and depends on how much electricity you use. That energy charge sometimes is related to what it costs to make that electricity at the power plant. And then sometimes that energy charge is got more charges built into it. Sometimes the distribution transmission charges, which is the next one we're listing, are included in what they call the energy charge. So we have to understand that sometimes these are all mixed up, but they're still in there. The distribution, transmission, or delivery charges are charges that are there predominantly to maintain the grid infrastructure. And so some utilities are splitting that out and saying, this is what it costs to make that electricity, and this is what it costs to deliver it to you, and together that's what electricity costs. And so in the example on the right, we have a general service rate schedule with a $25 fixed charge or customer charge, and they're being charged, in this case, 88 cents. I think we actually have a typo there, which is okay, but fairly high rate. That's not accurate. It should say 0.088. So in this case, it would be 88 cents. So we'll stick with that. But 88 cents per kilowatt hour. And they don't have a distribution charge, and they don't have any demand. So everything is built, everything is kind of hidden in that energy charge. And on the general service demand rate, because the general service demand are typically larger customers, they have a larger fixed cost, but a much lower energy charge. And so remember, that was supposed to be 8.8 cents or 0.088. So the energy charge is lower, but then they have this distribution charge that they are charging. So it's actually a total of 4 cents, this 3 cents and another percent. So the energy charge is 4 cents with energy, what it costs to generate it, what it costs to distribute it, distribute that energy, and then we have this demand charge. And the demand charge is based on the peak amount of energy used at a given moment in time. Could be a 15-minute increment. And so basically they're trying to look at worst case scenario planning and saying, what do I have to plan for when the most electricity is being used? How many power plants do I have to own to put that on? And so they're putting a demand charge in place to cover that. And so what you can recognize then is that demand can be very significant. But the other thing that's important is that when I'm generating my own electricity, I may not be influencing this demand, and I may not be influencing this fixed charge. I'm only going to be dealing in these energy and sometimes distribution. We're going to talk about that in more detail.
Uh, John, just a real quick point to follow up on your point with demand charge. An easy way to visualize why that may not, why solar may not impact that demand charge is if you just kind of think about when a facility has all of its equipment running and just kind of visualize a hog barn or a finishing barn that has a whole bunch of ventilation fans running. Well, just because the sun goes down doesn't mean that it's still not hot in the summer. And so those fans are still running, and most of those buildings, they'll run 24 hours a day all summer long. And so when your solar system quits working, that's when your facility would set its peak demand. And so you're still going to have, in most cases, a similar demand charge. And that's not always understood well by farmers that are considering this.
Right. And as we've discovered also, how they calculate that demand charge can make a big difference. And so, some research on an electric bill can be very enlightening. Let's cover this in a little, we're going to look at this a couple different ways so that we can kind of understand how we're charged for electricity and then how that influences the value of the electricity that's generated. In this case, we have an electric bill that is $98 for the month, for the billing period, where 800 kilowatt hours were used. In this case, $53 of that was the delivery, and 45 is the supply. And when we're talking about supply, that is the energy, what it took to generate that energy. And if we take the 800 or the $98 divided by 800, we recognize that the value of that electricity is 12.5 cents per kilowatt hour, or $0.125 per kilowatt hour. So we can definitely recognize that electricity is costing us 12.5 cents. Yet, when we break that apart a little bit, we can understand it a little clearer. This is actually that bill in its what we would read at home, and we can look at it in a little greater detail. In this case, the energy charges are the generation services that they're calling supply are $44 and $1.41. And so generation is actually 5.5 cents per kilowatt hour. And distribution, transmission, um, and in this case, the customer charge are adding up. And actually, we should be looking at just transmission and distribution as our delivery side charges cost us 6.6 cents per kilowatt hour. And so we can think about that if we are generating electricity at home in our at that location of our solar, we are becoming a generator. We are part of that supply. And so we can start to say that the utility doesn't necessarily want to value the electricity that we're generating at 12.5 cents per kilowatt hour. They want to say, well, you're just a generator. You're just that supply, and really we want to value it then at 5.5 cents per kilowatt hour. And so we do have to recognize that not only is there a desire to do that from the utility, but also a reason for that, where if we are just that generation, we are not actually doing anything to maintain the grid, so they don't want to pay us that value to maintain the grid when actually they're having that cost already anyway. So understanding those two different aspects are important. Let's look at it again from another rate schedule from Xcel Energy, which is a commercial, or which is a large electricity utility in part of our region. And I think I pulled these from Michigan, but Xcel is a Michigan company and may cover some other states as well. And particularly, I'm going to look at the two rate schedules here on the left. If I have a small commercial service, which could be a farm service, there's a customer charge, which is that base fee of between $11 and $16 a month. And then the energy charge is broken in half by distribution and supply. In this case, supply is 8.8 cents and distribution is 2.5 cents approximately. So about 11 to 12 cents per kilowatt hour for the electricity. And although the supply charge for this one is higher than the previous bill we looked at, we can recognize that this 8.8 cents is more likely what they're going to want to pay for that electricity than the full amount. In the case of this small general time of day service at the one on the lower left, this is an important concept because we're seeing more time of day rate schedules across the nation, because it's a way for that utility to gain the money when the electricity prices are high, but also a way to influence the customer to try to turn things off during times of high demand. And so you can recognize that the customer charges are the same, but then the distribution charge is the same, but the supply charge is off peak and on peak. And off peak, it's 4.525 cents per kilowatt hour. So in off peak times a day, electricity is really cheap. It's about 7 cents a kilowatt hour, and which is the 4 plus the 2.5. It's actually quite reasonable, and they're trying to incentivize you to use electricity during that time. Or maybe we could look at it this way and say they're trying to disincentivize us from using it during peak times. Peak times are typically in the afternoon in the heat of the summer. So July and August, maybe from 1 o'clock to 6 o'clock p.m. might be their peak time, and they're charging 16 cents a kilowatt hour plus another 2.5 cents a kilowatt hour during that time. So we have almost 18.5 cent electricity during that time. But here's the beauty of this type of a system for solar, is that solar tends to generate at its best in the afternoons in the summertime. And so we'd be generating our electricity at that time, and we would be replacing electricity that's worth 18 cents. And that can really help the economics quite a lot. And so in this case, even if they didn't pay for distribution, it would be worth 16 cents for this particular rate schedule. So what rate schedule you're on makes a huge difference. And in the case of a demand rate schedule, which is the one on this side, we can actually see that the cost of that electricity is 6 cents for almost all the electricity. And we start to recognize that if you're on a demand rate, it's going to sometimes the economics for solar doesn't look very good because of the lower cost of what you're producing. Again, we go back to the analogy of corn. I can produce a lot of corn, but if the price is really low, the economics aren't very good. And so in this case, this is like a low corn price here, and this would be a very high corn price. Let's follow this electricity just a little bit and give us a little bit of visual on what's happening at any given moment in time. We can think about this being a farm, and in the morning, the farmer starts to do some chores and turn on lights and pumps water and does a number of things. And he turns that load on, and the electricity is flowing from the grid because it's the morning, the sun's not up yet, and the solar's not generating. And it's pretty easy to imagine that that electricity is worth whatever his rate schedule says it's worth, full retail rate for that electricity. There's then also a situation where the sun starts to come up, generating electricity from the solar, and that solar then is also worth full retail rate because it is offsetting electricity that would have come from the grid. So it basically is replacing electricity that would have come from the grid. It's worth full retail rate. Then maybe the farmer, goes to his other job or to his other farm or leaves to run some errands, and things get turned off, and then that electricity from the solar is now flowing out to the grid. Electricity that flows out to the grid is called excess generation, and the value of that generation is really the overarching question of today's presentation, because it is worth, if we don't change, if we put this under the federal laws, and we're going to cover this in a minute, it may be worth as low as that energy cost of maybe 5.5 cents. But in the case of some other policies in the state, it might be worth more. And so that's what we're trying to figure out. So we're going to cover that in the next couple of slides. If you want to know what your rate schedule is, I would suggest the best way to do it is to pick up your electric bill from the farm that you're interested in and figure out what rate schedule they're on, and then go to the website of the utility and look up the rate schedule. The electric bill itself is sometimes challenging to get enough information to really understand what the rate schedule it fully is. And an example of that is my particular bill at my home does not include the fixed customer charge. It's not on the bill, and yet I am charged a fixed customer charge of $19 a month. But they simply tell me on my bill I use this many kilowatt hours, and this is how much I end up paying. They don't detail out any of the details, and so it makes it a challenge if I'm trying to figure out what the value of the electricity is from my bill. I have to go and look at my rate schedule. If you just want to look up and try to estimate it as best you can, this database, the utility rate database, there's a link to it at the bottom, does a very, very good job of having almost all rate schedules in the nation. Sometimes they might be a year or two old, so be a little careful to trust that this is exactly right, but there's a lot of them out there, and it really can help you search through and find rate schedules for particular areas if you don't have them otherwise. In the case of a state that does not have any solar policies that change the way electricity is billed, all states and all utilities are going to fall under the federal laws, and that is referred to as PURPA by many people, and that's the Public Utility Regulatory Policies Act of 1978. And before they had any of these other rules, we fell back on, this was the system of rules that we had. And it basically says, and I'm going to paraphrase, that all qualified systems, meaning that meet the safety requirements for renewables, have to be allowed to connect to the grid, and that utility has to pay for that excess generation. but that utility does not have to pay more than avoided cost for that electricity. And avoided cost has a definition, but you can kind of think of it simply as the energy charge. And what a lot of times it is the energy charge of what they would pay if they had to buy it from somebody else. So in that case, under PURPA, all that electricity going onto the grid is worth avoided cost or the energy charge. And so for our example, we're going to say that's 5.5 cents. And so worst case scenario, you fall under PURPA and they have to hook you up, and that energy that you send to the grid is worth 5.5 cents. So in Nebraska, I said 5.5, that's gonna be our example today. In Nebraska, retail cost for electricity is about 8 to 12 cents, but avoided cost rates are somewhere between 3 and 4 cents is what they're paying for, or avoided cost if we were under that system. Many states have applied a system of net metering, and that means they've adopted rules within the state that require the utility provider to calculate the electricity used from solar differently. In this case, they're going to use the word net, and what that is the net difference between what you use and what you generate, or what you send to the grid, the excess generation. And it generally allows the owner of the system to get credit for at least a portion of the electricity they generate. And depending on the size of the system, you should be able to get most of retail, if not full retail rate, for most of the electricity you generate under a net metered system, a net metered rule. And so we'll cover
John,
that. Yeah, go ahead.
just a quick note. So it's important to recognize that a lot of times net metering is going to vary based on the utility. And so specifically when you're comparing investor-owned utilities with, with maybe a municipal utility or a rural electric cooperative. And so, there's some instances here in Ohio where there's farms that may literally be right across the street from one another, but the way that we would evaluate their solar projects are very different based on the utility and their net metering rules.
Yeah, different states have adopted different rules, and there are some states that might require different rules for investor-owned utilities versus public utilities. In other states, the rule is across the board the same. And then also what I've recognized in Nebraska a little bit is how different utilities interpret and apply the rules slightly differently. It doesn't usually make huge differences, but it can cause some challenges if you're trying to do something slightly different. So we're going to cover a couple of those details here in the next couple of slides, but that does help, Eric. I wanted to just define the net a little bit clearer so that we understood. Here's the 3 different directions electricity can be going, and the electricity is going in these directions at any given moment in time in a particular system. It can be coming from the grid, it can be coming from the solar to the load, or it can be coming from the solar to the grid. In this case, I'm going to label the grid electricity A and the excess generation B. And really, when we say net metering, we're really looking at A minus B. And in the case of where A minus B is still positive, where our use was greater than what we sent to the grid, that B is going to be is basically equal to the value of A, because it's replacing effectively the A, so the amount of electricity that I use. So in this case, it's the net excess generation. So that net excess generation term is important. Where this gets interesting is when B is larger than A, and I have a negative value for that net excess generation. That's the situation where then the utility owes me for that excess generation, that net excess generation, and the policy adopted by the state or the particular utility of what that value is going to be important, and we got to get that value right in our modeling so that we can estimate the value of our electricity. This is kind of how it might work across a year in a particular system. And what we're seeing here is if we're looking at just the dark green, this is just how much that particular farm uses. And so this farm must have some heating load, or where it is doing some warming, or some high electricity load in the wintertime, because its maximum use is in the winter and it has less use in the summer. The yellow, on the other hand, is the solar, and you can see that it has lower production in the winter and more production in the summer. And then the light green is then the difference between those two. So this would be, the green might be A, the yellow is kind of like B, and we have the difference then. And so what we're seeing is that in the case of January, I just have a bill that is reduced, and all of my solar generation was worth full retail rate. The same is true for February, March, and April. But in May, I actually have overproduced with solar, and I have a negative value. And so then the value of this negative, then I multiply times the rate that my state my state or utility applies to that value. And I have another negative month and another negative month and another negative month, and then it's back to positive. And so um, let's talk about how that can be applied. The most common is to convert that negative value into a monetary credit. In Michigan, for example, they simply multiply that times full retail rate. So they would say that negative value times full retail rate for electricity is credited back to your bill on the next month. More common is less than retail rate, where you get some value, in this case, the energy charge. And I think that's what Ohio does, gives just the energy charge back, not the distribution or transmission charge, but whatever the value of the energy was. And then in Nebraska, they give avoided cost, which avoided cost can be the energy charge, but maybe a little bit less as well. And so again, avoided cost is kind of what they can buy it from the marketplace, uh, the low of the marketplace for that energy. Now, if you're lucky, in some states, they will allow you to roll it over as kilowatt hours. And in that case, if we just go back, I don't have the one where you roll it over, but I would take this negative 778 and I would apply that to the next month. And in which case I would get negative 1500, negative almost 3,000, negative 3,500. And then I would start eating away at that negative value over here, in which you can start to see I would use that up by November and December. And in that case, all of those kilowatt hours are guaranteed to be worth full retail rate. And so that is called annual net metering when you roll it over, but it doesn't exist in very many locations. More common are the monetary credit, rolling that credit over to the next month after paying out by how much net excess generation you had.
And one thing to keep in mind is, the details matter. So a lot of times I will hear this presented to farmers as, well, net metering is, it simply credits excess generation to the next month. But, and that may be true, but it's important to distinguish, is that credited as a monetary credit or a kilowatt hour credit? Because as John
Right.
just clearly explained, most of the time it's a monetary credit, but it's not always straightforward when you're listening to a presentation or reviewing a proposal.
Right. And if that credit, if we just go back to that again, if this credit is only worth 3 cents a kilowatt hour, what I may be thinking about in this particular situation is that maybe I need a little bit smaller solar array and don't want to generate these negative numbers, because it's hurting the value isn't as high. And so the size of the system can influence this a little bit, where we'd say, well, maybe we need to have this a little bit smaller. And so sizing the system has a lot of different kind of details that you want to bring into play. Some of it is your goals, how green do you want to be, but also the economics. So this is just a little bit of kind of maybe words of warning, reading the details kind of a thing. And these are a couple examples that Eric has run across, and you can add to this if you want to change anything, Eric. But you sign a contract with the utility when you hook these up to their grid, and the details in that contract can influence very much the economics. And in this case, this particular one says if the customer generator ever generates more than 120% of what they consume, then basically net metering is no longer provided. They can just cancel this contract, and you're going back to the federal PURPO arrangements. And
And
so they're trying to recognize that they only want these systems to offset energy, not to be true generators.
and where we were concerned with some of that in Ohio was we had a lot of systems at one point going in on, and some very large systems going in on grain drying operations, and which is very much dependent on the weather. And so as an example, there's a lot of fields here in Northwest Ohio never got planted this year. And so while you may typically be expecting a large load in the fall, electric load in the fall, some cases that might not be there. And so, this language caused us a little bit of concern or caution in some applications.
Right. If you had a warm, dry fall, you may not need as much grain drying. It'd be a good example of that as well. So. All right, there's another one, kind of another case study here, where this is something that also happened, where in the contract it basically says that the power company can change this whenever they want, and so you sign this contract and you do this model and this cash flow analysis for a 25-year time frame, and yet all of a sudden the contract can change without warning in many ways, and all of a sudden the economics are thrown on their head. An example of this, a version of this in Nebraska, is that there's a number of utilities that are only signing contracts for 10-year time frames, and the reason they are signing it for a 10-year time frame is they're suggesting if the policy changes at the state level in that 10-year time frame, they want to be able to not renew it and go back to something that is more beneficial to them. And so net metering policies are really put in place by states to allow for and incentivize some level of renewables, and that's why most states have put these in play. But the small utilities in particular have not always been super excited about these, and have tended to try to either thwart the net metering policy, or maybe try to weaken it, or try to get out of it as soon as they can get out of it. This is something that makes a lot of sense, but what we've seen is that many installers don't always include this, or they include it improperly, where there's an escalation of electric rates, there's an escalation or a time value of money. And what we see is that the electrical rates increase over time, and they increase over time at just over the rate of inflation. So if the rate of inflation is 2.5%, electricity rates may increase at about 2.5%, maybe 3 or 3.5%. It's not a lot over inflation, but we do see that they do increase over time. I actually got in an argument with my utility here in Nebraska, and they suggested that I should not model anything above inflation at all, and that maybe even I should say that their inflation is zero. And I said, well, why do you say that your inflation is zero? And they said, well, we haven't raised our rates in 10 years. And I accepted that that was true, except that in year 11, they raised them 12%. And so although they didn't like that I put a 2.5% inflation factor in my model, their inflation was zero for a number of years and then jumped a bunch and then was zero and then it jumped a bunch. And I said, well, if you want me to model that 12% increase on whatever increment, we can do that. But I would rather just say it increases a certain percent each year. It's simpler in many cases. But there's a lot of discussion out there, but the reality is we want to model an escalation rate, but model it that's correct. The other thing that happens more frequently is that rather than just ignoring it, a installer wants to make their system look good, and they will suggest a very high inflation rate. And they're doing that for sometimes reasons that make some sense, but mostly not. They'll say, you know, we're going to have carbon legislation in the future, and our electricity prices are going to skyrocket. So we should model this 6% inflation rate. Or they may look at some past data for a very short number of years. Well, look at the last two rate increases, and we see this 6% increase. Well, if we look back at the long term, that increase is much more reasonable in that 2.5 to 3.5% range. So if we model a inflation rate of 3.5%, electricity is going from 10 cents to 22 cents by 2040. But if we increase it at 6%, we're jumping almost to 40 cents by 2040. Now, 2040 is a number of years out. We don't know what's going to happen, but I really feel like being in this more moderate range is going to give us a more conservative look at what could happen. And this 6%, although is not likely, I have at times modeled both and told then the farmer that, look, the likelihood is we're going to be in this range down here, but if you think that's going to happen, let's look at it, but recognize that you're going to fall in that range. You're not likely going to be at that high end.
And one of the things that we've seen a couple times here in Ohio is, looking at, as you mentioned, historical numbers that are nominal. So they already include inflation. And then the justification of, well, we think that it's going to increase from, 3.5% to 7 or 8%. And, then again, that's a nominal number that has inflation. So now we've doubled inflation, and then guess what? We put inflation in the model. So now essentially we've applied 3 inflation factors to our energy escalation rates, which really causes it to get out of control pretty quick.
Right, and the example you gave last week, which was a 10% inflation for the first 10 years, and you start to recognize that we can really make these look good with some numbers that really probably aren't correct. And so we
Yeah.
want to be a little more conservative in that, so that we really can figure out if this is a good deal or not. This is the real fact of the matter, is that to maximize the value of energy of our solar system, we need to use that electricity. And because any electricity that we use by our load, our farm, our home, our business, that is worth full retail rate, and the utility can't do anything about that. That's where that full maximum is. If we give them the electricity through excess generation, there's all these things that can happen with policy that may reduce the value of that electricity. So the way to maximize the economics of these systems is to, in many cases, undersize the system, to size that system at 50 to maybe as high as 75% of our load and no higher. By undersizing that system, we're going to minimize net excess generation, and we're going to maximize the value of that electricity. And in the case where we're under PURPO or the federal rules, we may have to really severely undersize the system to get maximum economics. But maximum economics aren't always the most important factor. We can talk about this more later, but people's goals and whether they give value to it because it's green can influence that decision as well.
The other thing this does, John, is we maximize how much we're using, minimize. Let me rephrase that. So by minimizing net excess generation, you're also reducing your exposure to risk through policy changes, whether that's state policy or whether that's net metering policies.
Yes, very good. I'm going to turn it over to you, Eric, for the next half here.
All right, let me get my PowerPoint slides pulled up and give me a thumbs up when they look good. All right, John, can you see that?
I am seeing your I'm seeing all the slides. Now I'm seeing it in presenter mode.
We'll get there soon
Now I'm seeing
enough.
the whole thing. Good. There we
All
go. We're all
all
set.
right. Good. So yeah, so the second half of today's talk, we're going to look at kind of the impact of incentives. And one of the things that we talked about on Tuesday was, we looked at the price trends as it relates to these projects, and we recognized how we saw like a 66% decrease in the installation cost for commercial systems, from like $5.43 per DC watt to $1.83. Um, but with that, even with those declining costs, incentives still play a critical role to looking at a cost effective or a financially successful project. So I want to show a couple of examples. So we modeled a couple different simulations here, and as we look across the top bar here, you can see this would kind of be our best case scenario. So this is assuming a 30% investment tax credit, a 25% USDA grant, 100% bonus depreciation, and renewable energy credits. And we'll talk a little bit about each of these incentives in a minute. But that's kind of our best case scenario. Whereas then we modeled just the investment tax credit, and then kind of a worst case scenario where there's essentially no incentives available. Before we look at some of those metrics or the results, though, I want to briefly discuss the four common financial metrics that the system advisor model uses. So as you've heard John and I talk, simple payback period is a metric that a lot of installers and developers tend to point to. And simple payback's useful. I mean, the one benefit of that is it's certainly easy to calculate, but there's obviously some weaknesses as it overlooks the time value of money and variable and ongoing cash flows, and what happens after the payback period, those types of things. So uh, in addition to this, we really encourage folks to look at additional metrics, and specifically, we like to see a 25-year cash flow table, and discounting that cash flow table to present value. And so, really looking at a discounted payback period, and then also, what happens after that discounted payback period's reached in terms of our net present value. So those are the two metrics that we really like a lot, because it does take into account time value money. It can account for kind of the variable and ongoing cash flows, and and operations and maintenance as they may come in um, over the years, and your tax credits, depreciation, that type of stuff. So the other metric that's probably not used as much, at least in the lending sector, would be levelized cost of energy. And that's kind of an interesting one that also can tell us some useful information. The levelized cost of energy is essentially taking the total life cycle cost, so the cost of building and operating that system over the 25-year project lifetime, divided by the total energy production. And so in this case, we'd be talking about kilowatt hours. And so in a sense, it's eliminating a lot of the variables as it relates to rate structures and what the value of energy may be, because it's only looking at what's the life cycle cost versus your total energy production. And so As we look at our best case scenario here, you can see a simple payback would be 5.6 years. If we discount those future cash flows, it would be 7.2 years. Uh, when we think about levelized cost of energy, we're essentially looking at this saying, okay, is this less than what I'm paying for it? So if you're paying, 10, 11 cents a kilowatt hour, this would be great. We look at our scenario with no grant or depreciation or SRECs, all of a sudden just a 30% investment tax credit. It's not quite as clear here. Now we have a simple payback of 16 years. Our discounted payback, when we discount future cash flows, is actually longer than the analysis period. Negative net present value, and in many cases, this is probably equal to or a little bit higher than what most of us are currently paying. And then again, back to the comment of, these incentives are still important. While the costs have come down, I think that this last model here is really illustrating, yeah, the costs are coming down, but we still are fairly dependent on this 30% investment tax credit and depreciation and SRECs and these other tools that are available to help offset some of the cost. Okay, so we're going to talk a little bit about, I guess, what John and I have kind of tagged the cash flow mechanics of investing in PV solar. So the one thing that we need to think about when we talk about investing in solar is it's a significant upfront investment. So it's going to be a major capital investment that we're laying down on year one. The good news is there's low operations and maintenance cost, and the fuel cost is essentially free. Um, so how do we recover this initial investment? The first step would be our 30% investment tax credit. As we move on, then we would look at depreciation. Other incentives, grants, or loans, and this is going to vary, significantly, I guess, state to state, but also even utility to utility, as some utilities offer incentive programs that may not be available to others. Depending on if your state has adopted renewable energy policies that support energy credits, renewable energy credits, and in some instances can provide significant cash into a project. But then the interesting thing is once we get through here, so once we work our way through these first steps, we need to think about the balance. So any stack of cash that's still left from that initial capital investment, we have to recover with ongoing energy savings. And that's why it was so important to really understand the part that John just discussed with us in terms of how do we value a unit of energy we're generating. It really doesn't do us any good to inflate what we think the value of that energy is, because at the end of the day, it's we're only lying to ourselves. And so we need to make sure that we're accurately evaluating the cost, or I shouldn't say the cost, the value of those units of energy we're generating. So I want to spend a slide or two on each of these to just kind of give you a little more detail. The federal business energy investment tax credit program is a 30%, I guess currently a 30% tax credit on the eligible construction and equipment costs. So basically the system owner, the investor, obtains a dollar for a dollar reduction in their federal income tax liability. Now, to maximize the value of that tax credit, you can actually do a 1-year look back or carry it forward up to 20 years to monetize the full value. As you can see, the program's actually going to switch from a 30% tax credit at the end of the year to moving forward in 2020, it's going to drop to 26%. And then you can see in the table there how it's going to slowly stair step down to 10% by 2022. One of the things that I've come across a couple of times is kind of the idea of what's included in this 30% investment tax credit. So the idea of um, eligible property, I guess, has come up in the past, and essentially eligible property is that's necessary for the production of solar energy, and it's used as an integral part of the energy project. And so the um, the language actually specifically calls out this doesn't include buildings or structural components. And I've seen that before where some developers have suggested that, well, look, you can build the new building and we'll include that as part of the 30% investment tax credit. That doesn't necessarily work that way. It's also important to determine if cash incentives are subject to income tax. So in most cases, if you receive a grant, that's going to be considered taxable income. And as long as you're paying income taxes on that, you don't have to reduce the principal cost of the system before you take your 30% investment tax credit. However, if you have a grant incentive and you're not paying income taxes on that grant, you need to reduce the principal balance of the system before you calculate your 30% investment tax credit. So it's important to distinguish between the two, and it's always nice to have either a financial lending partner or a financial advisor, tax accountant, someone to help look at these proposals as well to make sure that they're being handled accurately. Depreciation's another incentive. So depreciation is essentially providing a tax deduction for commercial system owners. And generally speaking, we're looking at the coordinated reduction of the cost on a fixed asset over time that's designed to offset the revenue it's hopefully going to generate, right? Excuse me. Um, for most energy projects, including solar, we use the maker's model on a 5-year schedule to depreciate. Um, Another consideration as we think about depreciation and the investment tax credit, which we just talked about, is that if you utilize the 30% investment tax credit, which we just talked about, I'm not aware of, I've not worked with a project that didn't utilize the 30% investment tax credit. If you use that, you need to reduce the depreciable portion of your system by half the tax credit. So as an example, if we have a $100,000 project and I took a 30% investment tax credit, I have to reduce that by 15%. So 85%, or let's just say $85,000, would be the basis for depreciation on this project. And then finally, the Jobs Cut or Tax Cut and Jobs Act of 2017 set in place bonus depreciation, where you can have 100% deduction for the first year in a qualified energy project, set in place before January 1 of 2023. So bonus depreciation is available on these projects. I don't want to spend a ton of time on it, but I guess I do want to point out the questions worth asking. So just because bonus depreciation is available, it is optional. So just because it's available, should you take it? And I think that's a question, obviously between the farmer and their accountant that needs to be asked. Many times it's in the proposal development anyhow. It's often just assumed that, well, yeah, you're going to take 100% in year one. But in many cases, your accountants will kind of encourage you to kind of look at the long-term outlook for that farm or business, remembering that claiming a full deduction in year one means that you're going to give up deductions in future years against income from that asset, and it could actually work to your disadvantage in some cases. I think the key is to recognize that when we talk about depreciation, this solar project's likely just one piece of the farm's overall tax puzzle and their tax strategy. And so, every situation is going to be unique and applied differently. Other incentives, as we think about grants and loans, as I mentioned, often they're offered through federal, state, sometimes local government, or even utility companies. The most common grant incentive that we deal with, especially in the ag sector, is the Rural Energy for America program that's offered through USDA. But it's certainly worth contacting utility to see, do they have other programs, or as mentioned, some states have specific programs as well. As mentioned earlier, I really don't like to see grant programs assumed in a financial proposal. Oftentimes those grants are taxable income, so we need to account for that in our cash flow table. And then again, many times they're not guaranteed. And so to just assume that it's going to be funded is often a little bit misleading. I did mention the REAP grant program. Again, that stands for Rural Energy for America program. And it's a 25% grant program not to exceed $500,000, which is often not a problem for the types of projects we're talking about on small farms. They also have a loan guarantee that can cover up to 75% of a project. This program's not for residential purposes. It is a reimbursement grant. It's not upfront money. So if they're trying to finance $100,000 project, it's not 100,000 minus 25%. They need to finance the whole thing, and it is reimbursed. And again, it is taxable income. And in Ohio, we tend to fund anywhere from 30 to 35% of our actual proposals get funded because it's a very competitive program here in Ohio.
I want to add just a second to that REAP. One of the things that gets asked a lot is that if this has to be a rural business or a farm, but the house can be on the farm, but 51% of the energy use has to be done by the farm and 49% by the home or less. And then they'll they'll prorate it to the farm's use, because this is for rural businesses and farms, and rural is any city under 50,000. So a lot of our states are rural, even though we think about them as more urban. So under 50,000 people is rural.
That's a great point.
And then the last thing I'll say is that there's some people that will want to apply for the REAP grant, but they are doing the project regardless if they get it or not. They're just hoping for it. In that case, you need to apply for the REAP grant and get the application fully submitted prior to buying any equipment. Because if you've submitted and then you buy equipment, it can count. But if you've bought equipment prior to submitting, that can't count. So this is for people that would be building the project regardless of the REAP grant. If you need the REAP grant to build a project, you should wait till it gets approved prior to buying any equipment. So just some notes on the REAP grant.
Thanks, John. All right, so I want to talk a little bit about solar renewable energy credits. And again, this is probably something that many of us are not as familiar with. An SREC, or solar renewable energy credit, is essentially representing the environmental attribute of solar electric generation. And it's not bound to the unit of electricity that is generated. So it's kind of it's just representing the fact that electricity was generated from a renewable energy source. So while the phrase green energy gets thrown around a lot, the electrons aren't necessarily green. So there's no way that we can tell the difference between electricity from our coal generators versus a solar project. So we need to have a tracking mechanism to differentiate this. And it really goes back to state level renewable portfolio policies or legislation. And so, currently there's 29 states that have a renewable portfolio mandate and an additional 8 states that have renewable energy goals. In these states, utilities can either so in general, these policies are mandating our utilities diversify their electrical generation mix, and and so they can do that in a couple of ways. They can actually own and operate a system that is certified renewable project. So as the owner of that, they're gonna have the renewable energy credits from that, or they can actually purchase credits from other systems that are installed. And so if you're a farmer and you've installed a system on your farm, for every megawatt hour, if we look at this second bullet point, that system generates, you're going to have a renewable energy credit that says, look, this system generated a megawatt hour of solar energy. That credit could be purchased by other utilities to stay in compliance with that state level policy. So it's a fairly complex system. There's a number of different ways that you can actually purchase or trade credits. And some instances we'll see that done up front. where aggregators or developers or brokers will say, hey, we'll buy all of the credits for the 25-year life cycle of your system. In 2012, I saw some farms in Ohio that were getting paid $30,000, $40,000 for all of their SRECs over the lifetime of the system. Today, SRECs are worth anywhere from $5 to $25 a credit. So you can also sell those kind of in real time as they're generated. If we look at kind of the weighted average price of SRECs over time, and this is looking at all of the states that will be located in the PJM regional transmission interconnect, you can see that, in general, we've seen kind of this downward trend in terms of the value of our renewable energy credits. That's kind of driven by two things. It's driven by one, what is the non-compliance penalty payment? So if you're penalized $600 for not being in compliance per megawatt hour, you're not going to pay any more than that for an SREC. The other thing that's going to influence this is simply supply and demand. If we look at kind of filtering this down to Ohio and Illinois, supply and demand in Ohio, which is up here in this dark brown. In 2009, there were 14 certified solar projects in Ohio, and today there's more than 2,700. So as we think of supply and demand, it's also going to have downward pressure on the value of those SRECs. The other wild card that could change that, and that's one of the things we saw here in Illinois, is policy. So they enacted some policy that set a value for their SRECs that was relatively high. As in closing, so then we kind of get back to after SRECs, anything that's left over, so any money that we still haven't recovered from that initial investment, has to be done through energy savings. And this is just kind of a reminder from what John mentioned. We need to understand how we're compensated for net excess generation, and B, in many cases, work our best to minimize net excess generation. That's kind of our last slide. At this point, this is, again, kind of a reminder that next week, John and I are really going to spend a lot of time helping you construct a simulation model using the System Advisor model. And we're going to look at how that modeling tool brings together production and system design characteristics with your financial assumptions, and how those different variables are going to influence our financial metrics. So at this point in time, John, I don't know if there's anything in the chat box, but I'll let you kind of take over handling the Q&A.
Yeah, any questions, we're willing to take them now. Feel free to type in the chat box or unmute yourself and ask. We will be putting together the video or the recordings of these presentations and send you the links of those. Hopefully we'll get the first two of those out in the next day or two here. I think I should have the first one done today. We're just doing some minor editing of those. Also, we will have the PowerPoint presentations of these if you'd like them. We can either send out a link to those, or we'll put those up on the SARE website and send out a link to that. So we're glad to join you. We are going to go over some case studies on next Tuesday, so hopefully you'll join us, and we'll be using some real data to look at kind of the cash flow analysis for a solar array in an Ohio swine farm. So that'll be our example, and we'll be able to go through our model and show you how that works. And then on Thursday, again, as he said, we're going to play with that model a little bit and try to do some optimization exercises, and how do we try to optimize for different characteristics. Maybe that is pitch and tilt and other things, as well as trying to maximize the economic financial attributes. So